What's up? We are now in chapter 4. We're going to be talking about circuit theorems. This is probably one of the most powerful ways to look at circuits. It's outrageously powerful. And it's actually easy to write down. But anytime you have something easy to write down, that means that you have to really understand it conceptually. So what you're going to find here is that this chapter deals with circuits in a conceptual manner. Whereas node and mesh is really just ugly, right? You know, hey, you could write it down easily. I'm not saying that you can't, but it's just ugly because you got to solve all those systems of equations. This chapter doesn't do it that way. You know, it kind of reminds me of Star Wars, right? What do the Jedi say about the lightsaber? They call it what? The elegant weapon. This is what this is. This is the elegant weapon for analyzing circuits. And it is probably one of the most important things that you're going to learn from me. Because when you cannot use mesh and node, you're going to rely on some of these sources, source transformations, to really explain what is going on here. Yes, you would be, Angel. So now moving on here, what are we going to do here? You're going to see that there are 4 theorems here. Okay, we're going to look at 4 theorems. You're going to be looking at something called you're going to look at superposition. We talked about superposition in the first chapter. Okay, you're going to find that there's these things called source transformations. That means you'll be able, there's a way, if you set it up just right, to convert a voltage source into a current source and a current source into a voltage source. It's a pretty nifty little transformation. And then we get to the most important concept in this chapter, Thevenin-Norton equivalence. This is without doubt, the most important concept. And then there's this little tiny theorem called maximum power. But you'll see that it's your ability to deal with Thevenin and Norton is the most important thing. It's a really, really beautiful theorem in circuits here. And I won't go into any more detail here, but I'll give you an overview here in a minute, but that's really what we want to do here. So what I want to do here is that I want to start off with the first one of these here. So what we're going to deal with is the first one that we're going to deal with is called a Thevenin-Norton source transformation. So there are transformations exist, particular transformations that convert maybe I should do it this way, that convert current sources into voltage sources, or vice versa. And the key here is that it has to be very particular. So how do I actually see this thing here? So the key here is that they have to look like this. You have a voltage source that's typically called a Thevenin voltage. And if I have a resistor in series, this is known as the Thevenin resistance. And what you find here is that you can have a load right in here. And that load is arbitrary. Okay, and so what we want to do here is I'm saying that there's a way of making these two equivalent. And there's a current source, which is known as a Norton current source. And if I have a resistor that's parallel to the current source, this is known as a Norton resistance. And if I have the exact same load, there's a way to make this guy equivalent to each of these. How do I do that? Well, if they're equivalent, then that means that the current flowing into that load or this load must be exactly the same. And if they're truly the same, then that means that the voltage across this load in each case must be exactly the same. The only way these guys can be equivalent is if the load gets the same current and same voltage here. So the only way these two circuits are equivalent is if the load sees the same incoming current, I, and same voltage V across it. That's the only way it makes any sense whatsoever. So what we'll do here is that there's a way that you can derive this thing here. So to derive this, apply KVL and KCL. Okay, so if I look at the Thevenin circuit, what we're going to do here is that we're going to apply KVL, and if I look at the Norton circuit, because it's in parallel, I'm going to apply KCL. So here we go. So what we're going to do here is that I'm going to apply KVL. So that means if I know the current, I know the polarity of that resistor. And right away, what we can write here is that we could, so if I make this loop here, you could see here is that the Thevenin voltage must be equivalent to both of these, or I can write that V is going to be VTH minus the current through the Thevenin resistance is I, so therefore its voltage has to be I RTH. Now, if I look at KCL here, you could see here is that the source current must also be equal to the current that's going down the branch of this guy here. So in other words, that if I apply KCL, what you're seeing here is that you're seeing that the current I should be the Norton current minus the current across the Norton resistance. But I can rewrite this guy in a way that, since I know what the voltage is, it's got to be V over Rn. And that's what that current is. So what you're seeing here is that I have two conditions. So KVL sets this condition. KCL sets that condition right here. So what I'm going to do here is that the only way these could be valid transformations, if I here for the Norton circuit must be the same for this guy here. So what I'm going to do here is that I'm going to solve for I. Since I already have it in I, what I'm going to do here is that I'm going to solve for I in this equation. And what I'm going to get here is I'm going to get that what? I must be what? It has to be VTH divided by RTH minus, let me make sure I get my sign right, V divided by RTH. So if I do that, look what I get. This implies that if I have on the left side, I have VTH over RTH minus V RTH. And then on the right side, I'm going to get IN minus V over Rn. So this is the condition in order for these transformations. So what you can see here is that this term says that the only way these two terms can be the same here is if Rn and RTH are exactly the same. Okay, and the other condition is this guy right here. The only way you can make this condition here is it says that IN has to be the same as VTH divided by RTH. In other words, the necessary condition for a source transformation is RTH must be the same as Rn, and VTH has to be RTH times I Norton, or R Norton times I Norton. This is the necessary conditions here. So as long as I do that, then there's no problem. So in other words, I have a Thevenin-Norton source transformation. So a Thevenin-Norton source transformation is this, that if I have a resistor and a voltage source in series, and if I have a current source with a resistor in parallel, that if this is value VTH, RTH, and this is IN, and this is Rn, these two are equivalent to each other. And this is what they call a Thevenin circuit. And this is a Norton circuit. That is the source transformation. So with this source transformation here, what we can do here is that now we can apply this to circuits and actually get, be able to simplify our circuits here. So let me go get the circuit that I want here. And let's go practice this. So I want to apply source transformations to actually solve this circuit here. So here's our example that we want to apply this to. So the first thing that we should look at here is we should look at what? Well, for starters here, note that we want to solve for the 3 ohm resistor. So the fact that we want to determine the current of the 3 ohm resistor, this implies that the 3 ohm resistor cannot, be touched in the circuit with source transformations. So that means I can use everything else. I can reduce anything else except that one resistor right there. Okay, so let's go do that. So the first thing that I'm going to do here is that note that I have a current source. I'm going to focus on this part of the circuit here. So if you go and you look at this circuit here, what I'm really going to look at here is I'm going to look at this guy right here. So if I paste this guy in here, what I'm going to do here is that you can see that in this circuit, I have this guy right here. I'm going to focus on these guys right here, because I could see that those guys are in parallel. So what I'm going to do, I'm going to do a source transformation on these guys here. So if I do a source transformation, what does that look like? Well, if I do that, then that means I do this here. I'm going to come here. So I have a 10-volt source. Then I have my 3 ohm, which I'm going to leave all by itself. So I have 6 and I have 3. And here's my current that I'm looking at. So I'm going to change that. So what I'm going to do here is I'm going to change that in such a way that it's a voltage source and a resistor in series. So when I look at this guy here, I'm assuming that that's negative and this is positive. So then check it out. Then I'm going to come in here and I'm going to replace this guy with what? A resistor and a voltage source in series. Look at the polarity. This is minus, this is plus. So then this is my 8 ohm, and then I just apply Ohm's law. So how do I get the voltage? Using a resistance and a current, I multiply them together. So this is going to be 16 volts. And then I get my next resistor, which is right here. So I just did a source transformation. You can now see here that I have a 8 and a 4 that are in series here. So now what I'm going to do here, so I really have what? I have 8 and 4, which is 12. So I got 12 and 16. So now I'm going to do another source transformation. And my source transformation is going to involve which one? Actually, it's going to involve this guy right here. I'm going to convert to a current source. Resistor combination. Now remember, when I look at this thing, this is 8 plus 4, so that's a 12 ohm resistor. And then I have a 16 volt source. So note, this tells me that now my Thevenin resistance, which is the same as my Norton resistance, it's 12. So this has to be the same as my Norton. But if I want my Norton current source, then it's got to be the Thevenin voltage divided by the Thevenin resistance. So in this case, it's got to be 16 divided by 12, which then should give me, let me make sure. That current source should be 4/3. For some reason, I couldn't do the algebra in my head here. So let's go do that. So if I do a source transformation here, what does it look like? Well, my source transformation now looks like this here. I have my 10-volt source. Here's my 3. Here's my 6. I know that this is my current right here. So now I'm going to convert that to a resistor in series and a resistor in parallel and a current source in parallel. So then here I go. What's my Norton resistance? In this case, it's got to be 12 ohms. What about my current source here? Look at the direction of my current source. That current, if I look at that current should be going in which direction here? Well, I'm assuming that the current is coming in this direction right here, right? Because that's the direction of the current that was coming out here. That's what my guess is. So I got to keep assuming this. So then that means I'm going to have a polarity where my current source should look down like this. So it should be minus plus, and this guy should be 4/3 amp. Okay, so now if that's the case here, now you could see that I could now convert these guys in here. So in this case here, what am I going to do? I'm going to convert to a Thevenin source circuit. So if I do that, we could see that 6 and 12, that must be a 4 ohm resistor, right? It's got to be a 4 ohm resistor. So if this is the case here, I'm going to have a 4 ohm resistor, and then I got to get my voltage source here. So I know that R Norton is a 6 parallel to 12. So that is a 4 ohm resistor, which is the same as my Thevenin. Then I need my Thevenin voltage, which should then be R Thevenin times I Norton. So in this case, it should be 4 times 4, 3, which give me 16/3 volts. So here I go. I keep with my source transformations. And I know that this current is still going in this direction. And here's my 3 ohm resistor. So now what I've done here is that I go to a resistor, a circuit that looks like this now. So I have a resistor, then I have my source. According to our polarity, it's got to be plus and minus like this here. You know what? I'm going to move this down a little bit. Or actually, let me move this guy over. So if I do that, you could see that this guy's really what? A 4 ohm. And this guy's going to be a 16/3 volt. So now I have a series circuit. So I have a series circuit. So that tells me here is that I have what? I'm going to use Ohm's law. I know that series elements have the same current. So I know that according to Ohm's law, it should be the voltage. Note that these guys are in the same direction. So it should be 10 plus 16/3 volt is then going to be the resistance, which is 3 plus 4 ohms times the current of the 3 ohm resistor. And if I compute that, I get that the current of the 3 ohm resistor should then be 2.19 amps. And now I have my current using source transformations. Okay, that's how you can use source transformations to simplify your circuit. Now, the rule of thumb that I typically look at, if I'm trying to I'm going to use source transformations, a lot of times, if I can't figure it out in my head, unless I see it like really importantly, where I feel like I really have to do that, I typically won't do it. I got to be able to do things in my head so that I can move through it quickly. So that's sort of like the way I look at it. Let's go to the next one. So the next one is superposition theorem. This is an incredible idea. It's almost unbelievable. It's so unbelievable that your PLC is about wiring and using the superposition principle. Now note, I'm going to give you an analogy. Imagine that you have, so when you look at Newton's second law, Newton's second law abides the superposition principle. And what I mean by that is that if I have a series of forces acting on an object, right, I can sum all of these forces, and the sum of all of these forces is what we call the net force. In other words, there's only a single effect acting on an object. Now, forces, when you look at the net force, objects do not feel individual forces. They do not feel individual forces. What they feel is they feel the net force. That's what they feel here. In essence, that's exactly what circuits do. Circuits don't feel the individual sources. What they feel is the sum of the sources acting on a particular resistor. And this is what superposition principle is for circuits here. What it says here is that the current IR through some element is the, how is this, the current IR is the algebraic, let me make sure I'm thinking about this correctly, is the algebraic, I'm going to move this down a little bit. Is the algebraic sum of all currents produced independently by each source. In other words, if I want the current to cross, let's say, some resistor, then I'm going to have that there's source 1 produces a particular current, which is called I1. And then I have source 2, it also produces a particular current. And depending on how many sources I have, each source is responsible for producing a current through that element. But this is slippery the way I'm saying it. And what we're going to see here is that it's really the sum of all the sources will contribute to this thing right here. And this is really, I'm not really saying it elegantly here because I should be doing a much better job of saying this. But let me see if I could give you a sense what I mean by this. So the first thing that you got to do here is that, so remarks here. 1. The first thing is that one has to isolate one source and deactivate all other independent sources. So that means what I'm really saying here is that if I want to focus on, let's say, so when I say isolate one source here, that means, let's say that I focus on source 1. So I'm going to look at the current produced by source 1 only. So we focus on that one and make it the only source in the circuit. Even though there's a whole bunch of other sources here, so this means here is that we must kill off all other sources to see the effect of source 1. Because if I had other sources, they're screwing it up. So how do I kill off sources here? What we do here is that we short out voltage sources. What we do here is that we short out voltage sources and we open current sources. So, okay, that's here. So how do we do that? Well, so to deactivate sources, we take a voltage source then, and then what we do here is that then we replace it. We replace with a short. So whatever the circuit is, what we're going to do here is that when we replace it, we're literally going to come in here and we're going to literally put a short right where that voltage source is. Okay, so you're literally going to deactivate the source by putting a short there. And what if I had a current source? In a current source, what we do here is that you could imagine that I have a current source like this. Let's say that that's the way that current source. So what we do here is that we do the same type of thing. We replace this guy. And the way we replace it here is that we come in here and we replace it with an open. So when I go and I look at this current source now, it's a hole. So there's nothing there. That's the way you deactivate the sources here. So in order to see that, I want to go in and I want to look at an example. Okay, using the same kind of thinking here. So let's go to this example. So let's look at that. So when I'm looking at this circuit here, what we're doing here is that we want to go in and we want to use superposition to really look at this guy here. So what do I mean by this here? So what I'm going to do here is that I'm going to do the following thing. I want to look at the circuit in particular here, and what we know here is that we want to calculate the current through the 20K resistor, right? So our goal is the current through the 20K, which is the same as IX. But what you're seeing here from the viewpoint of superposition theorem, all three sources will contribute to IX. Okay, all three sources will contribute to IX. So superposition says that IX is really the current produced at IX by the 12-volt source, by the 3 milliamp source, and by the current produced by the 9 milliamp source. But in order to see these individual sources, we have to kill off all of the other sources here. Okay, so here's what we're going to go do here. So what I want to go do here is that I want to go in, I want to look at this thing source by source. So here I go. So what I'm going to look at is that I'm going to look at the response of IX due to the 12-volt source. So we know that there's a current that's going to be flowing at this point here. So what I'm doing here is that I'm going to take my circuit here. So here I go. And I only want to look at the effect of the 12-volt source. So what I'm going to do here is that so this implies here is that I must deactivate the 3 milliamp and the 9 milliamp sources so that I only see the effect of the 12-volt source. So then I come in and I'm gonna kill off my current source by putting an open here. Then I have my two other resistors. And then I'm gonna kill off this guy right here with an open here. And so when you're looking at the circuit here, you can see that this is my 12K, this is my 4K, and then this is going to be the current of what? Of the current produced by the 12-volt source. So right away, you could see that I only have one loop, right? I only have one loop in this circuit. So that means then that everything's in series, but you could see that the 12-volt source is going to produce a current in which direction? In the opposite direction. So I know that there has to be a minus sign. So if I look at that current here, then the current produced by the 12-volt source should automatically have a negative sign because it's an opposite in direction. So here I go. Using Ohm's law, it's got to be what? It's got to be all the resistors in series divide, my bad. All the resistors in series divided into what? The source. And when you compute this thing here, you could see that that's 36. So I got 12 over 36. I'm going to get negative 1/3 milliamp. And that's the contribution of the 12-volt source to IX. So then I go and I do the exact same thing. So now I'm going to focus on the effects of the 3 amp source here, 3 milliamps. So the response of IX due to 3 milliamp source. This tells me that I got to do what? I have to deactivate all other sources. So I have to deactivate the 12 volt source and the 9 milliamp source. So let's go do that. So if I do that, what you're seeing here is that again, I have this guy. And I know that that's the current that I want. So what do I got to do to the voltage source? I got to short it. Literally put a short there. And you're going to see what I'm going to ask you to do in lab this week. I'm going to say where you see the voltage source, put a short across the voltage source. And if you take a short across the voltage source, then all of a sudden, you're going to see that you're going to come in and I have an active 3 milliamp source. And then again, as we did before, we had the 4K, 6K, and I still have my open for the other current source. So that means that this current here is going to be the current of the 3 milliamps that contributes to this. So then what am I going to do? Well, you could see that I have 2 parallel resistors. So what am I going to use? I'm going to use CDR to get I of the 3 milliamp source here. So here I go. So I want the opposite resistor to 20. So that should be the 6. So I'm going to get what? So I have the 4 plus the 6 divided by the sum of the 2, which
That 6 should be a 12.
That 6 should be a 12? Okay, thank you. So then this should be 4 plus 12, and then I'm going to get 4 plus 12 times 3 milliamps, and the value that I get here, so I get 16, what is that, 36? I believe that's 4/3, right? 48, yeah, should be 4/3 of a milliamp. So that's the contribution to from the 3 milliamp. And then finally, we have one more. So I'm then going to have the response of IX due to 9 milliamp source. And so, of course, I have to deactivate the 12 volt and the 3 milliamp source. So now that we sort of like hopefully get a sense of what's going on, I'll move a little bit faster. So then I have what? I have the 20K. And so this guy's my short, this guy's my open. And then I have 2 resistors right here. And then I finally activate my source. In this case, I have a 9 milliamp. And so this should be a 12K, 4K. And again, this is a short right there. So clearly, when I'm looking at this current, this I have to keep the same direction. This is going to be the contribution to the 9 milliamp. And you could see that that 9 milliamp is going to give you a negative contribution. So if I look at this thing here, what I'm going to use again is I'm going to use CDR to get I of 9 milliamps. So right away, I could see that this current here must be negative. So 9 of the milliamp right away has to give me a negative sign because it's going against the flow. So it's got to be the opposite resistor. So the opposite resistor in this case is what? Is the 12. So I'm going to get 12, and I'm going to have 20 plus 4 plus 12 times 9 milliamps. In this case, I end up getting minus 3 milliamps, and that's the contribution to the 9 milliamp to that 20K resistor here. So now I have 3 currents. So what does superposition tell me? Then superposition says that if I want the current across the 20K, it's going to be the contributions of the 12 volt, the 3 milliamp, and the 9 milliamp, which then gives us that you're going to find a value that this is going to be minus 1/3, 4/3, and this is minus 3. And when you compute this, you get minus 2 milliamps, and that's the current through the 20K resistor right there. That's superposition. What is the PLC this week? You're going to have a circuit that has 2 sources. You're going to ask to literally deactivate the sources so that you can actually see the sum of these guys right here. Okay, so we have now looked at 2 of the 4 theorems in this chapter. The 4th theorem, the power theorem, is a tiny little theorem. But this is the most important piece without any doubt. So I'm going to come to Norton's theorem later. In this chapter, I'm going right to Thevenin's theorem. Once I've thoroughly introduced Thevenin's theorem, then I will bring in Norton's theorem. You know, I love the history of science. You should, if you get a chance, you should read about the history of Leon Thevenin and how he actually really changed how people look at circuit analysis. So here we go. The goal of Thevenin's theorem is to identify and separate a portion of a complex circuit. Okay. The goal of Thevenin's theorem is to identify and separate a portion of a complex circuit. What do I mean by that? What I mean by this is that you're going to look at a circuit, and let's say that this is your circuit right here. You have a circuit, and what you note here is that somewhere you notice that there's a piece which we call the load circuit. So this guy right here is sort of like what I call the subcircuit. And what you're seeing here is that in this circuit, you're finding that you really want to find out about the load. Okay, and so in this circuit, I call it the load. And what you're interested in here is that you want to calculate something about the load circuit. But the problem is the subcircuit is there and it's really complicated. So what you do now is that you literally separate out the subcircuit. So you identify this and now you separate out the subcircuit in order to simplify. using Thevenin's theorem. So, that subcircuit can be really complicated. It can have numerous sources. It could be, ugly as hell. And it doesn't matter. So all of a sudden, you have this subcircuit now. And the whole goal of the subcircuit is that now you want to create what is called a Thevenin equivalent. In other words, we want to replace this very ugly thing by this very beautiful subcircuit, which is a voltage source and a resistor in series. And once you simplified it this way, what we do then is that now we reconnect it. The Thevenin equivalent to the load and solve the circuit problem. In other words, we now go in because we can't tell the difference between these two circuits. And so that means I literally come in here and I go back and I reattach the load now. And when you look at this load circuit here, what we say then is that this is a much, much easier problem to solve. Much easier problem to solve. And so what happens here is that we have to apply a procedure. Okay? We have to apply a procedure. And what I'll do here, instead of writing it down, I'm just going to show you what's written in my notes. And these are what I call the Thevenin rules. And there's really 3 techniques to dealing with this. Okay, there's method 1, there's method 2, there's method 3. It turns out that method 3 is not used, only by electrical engineers. And it's something that you really, really have to learn. And you'll see here is that method 1 is about independent sources only. Method 2 is about independent and dependent sources only. And then there's method 3. Method 3 has no sources in the circuit. And that might sound a little bit crazy, but it isn't. And I'll leave it there for right now for a later on discussion. So what's the idea here? The idea is that we want to apply, Thevenin equivalent rules to understanding what is going on here. And so the rule goes like this. The first thing you got to do is that if you have a Thevenin equivalent, right? A Thevenin equivalent implies that you need VTH and RTH. How you calculate VTH is the same regardless of which method that you actually use. Okay? This The Thevenin resistance, there are two possible ways. Here, there's only one possible way. So what you're seeing here is that A is about calculating Thevenin's voltage, the Thevenin voltage. B is about using two techniques. Method one, which I really never want to see you use this on a quiz or an exam, unless we're talking about the next chapter. When we start dealing, not the next chapter, but when we start dealing with AC, when we start talking about capacitors and inductors, that's the only time you should be using method one. Method two is what you're going to see on quizzes and exams. So you want to be very, 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 very careful how you do that. So the important one is method two, not one. So why the hell even talk about method one? It's conceptual. It's a powerful conceptual model. And when you look at a circuit, I will guess that 99% of the time, if not 100% of the time, you actually don't see the circuit, you see a Thevenin circuit. That's the important piece right there. And that's why I'm going after method one, because that's really the language that people use for circuits here. But I'm really out of time, so I can't move on here until then. Okay, you guys got a quiz on Wednesday? Homework turned in? Good luck to you. I'm sure I'll be seeing a shitload of you guys tomorrow and Wednesday. I look forward to hanging out with you guys in office hours. Okay?
Love you, Carlos. Have a good one.
Okay.